Hi everyone. Can you hear me? Yeah, probably. So I'm Gargi and I'm going to be talking about system calls and system programming. So before I start, this is kind of inspired by Liz Rice. She does a similar talk about Go and what are system calls and how you do them in Go. Uh, and I'm going to be talking about Rust because, of course. So I would be remiss not to mention the Recurse Center where I learned about Rust and talked to a lot of other people who are doing Rust. And you should check it out. It's an amazing community. And before I start off on Syscalls, I want to talk about what even is a systems programming language. It's a word that's thrown around a lot in context of Rust. Like Rust is this systems programming language which allows you memory guarantees, blah, blah, blah. It's like, okay, what is a systems programming language? So let's go back to the 1970s because, of course, we'll have a history lesson. So there's this paper in 1972 called Systems Programming Languages, and it says, a systems program is an integrated set of programs, and the programs form a greater program that work together, and they're big in size and they're complex. So typically something which is multi-programming or translating or simulating something or time sharing would be an example of the systems program. And then it goes on to define the properties of a system. So it has a lot of sub-problems. There are more than one people working on this problem, and it's evolving with time, and it's for production use, and it's not solving one single problem, and it's continuously evolving, and etc., etc. So that's okay, I can get behind that, and that's a very descriptive definition of a system. But the key idea behind this paper was prescriptive. So this is a time when you had assembly language, and you were trying to distinguish between assembly languages and like other languages like Fortran. Yes, 1970s. So it says, when you were writing assembly, you were doing this bit fiddling, and to get out of that, you would use systems languages, which will allow you to write programs that are that allow you to interface with the hardware and the operating systems, but still are high level enough that you don't have to do bit fiddling, and the debugging time and the writing time and all of that is minimized, even though you're not doing system intensive computation. So then it goes on to say that before you had assembly, you had primitive operations where you had on-off switches for instructions, and then people said, oh, but we want more. And then you got to assembly, and then you wanted to write Fortran. And then the compilers couldn't understand what the languages were without the aid of systems program. So we did get to a definition of what systems program actually are, or like get examples of what systems program actually are. So you have the compilers and the loaders and the macro processors and the operating systems. So okay, I have an example now. So that makes me understand a bit more. And then it was the 1990s, and it was the rise of scripting languages like Python and Bash and PHP. And now you have a clear separation between these languages. So you would say systems programming languages are languages where you write data structures and algorithms from scratch, and which allow you the access to hardware and memory, and you can do things there. And versus systems language versus scripting languages are designed for gluing. So you'd have systems programming languages which are strongly typed, And because they're strongly typed, they help you manage complexity, versus you have scripting languages, which are typeless so that you can glue things together faster and have rapid application development. But then it was the 2000s, and things were getting better because, yay. So in the 2000s, in the 2010s, you have Dropbox, which is built, all of it is in Python, and that's very large and scalable. And then you have JavaScript, which is used to build all of the web. So you have a lot of engineering resources which are being poured into writing just-in-time compilers for Python and JavaScript, etc. And the performance, even though it's not as good as systems programming language, it's highly competitive. And then you get to, so there was this panel in 2014 where Nico Matsakis, who is on the Rust core team, and Andre, who wrote a D, and they were asked, like, what is a systems programming language? And Nico says, oh, like, Go is not a systems programming language. It's written for the server, it's not client-side, it doesn't care about safety, it doesn't care about security. So, okay, cool, thanks. And then you have Andre, which says, a systems programming language must allow you to write your own memory allocator in it, and you should be able to forge a number into a pointer because that's how hardware works. So a good rule of thumb would be, if you have an efficiency problem, how much freedom do you have to solve it? So the wonderful part about systems programming languages is that once you identify an efficiency, is it within your power to eliminate that bottleneck? Do you have control to eliminate that bottleneck? So in the same way, when you have statically typed languages, you have the confidence to say, oh, if I'm adding these two integers together, I'm sure they're integers. If you have a systems or like a low-level language, you have the confidence to say, this code will execute on the machine as I specified. So today, so systems programming today is to identify that whatever language you have, does it allow you to interface well with modern hardware? And Rust does this really well, but it borrows the ideas from like functional programming principles for error handling, memory safety, etc. But if you want to throw all that away and you want a very precise definition of what systems programming is, it's when you spend more time looking at man pages than reading the internet. Cool. So with that behind, I want to talk about how do you do systems programming, or what's a good way to do it? I think I want to demystify it and tell you it's simple. So what is a system call? So let's say you want to open a file. But you want to do it from your user program, but you don't have the permission to open a file, because then you'd go into the hardware and load the file from the disk to the memory, and all these privileges are the privilege that your operating system has. You don't have those privileges. So you in the user land will call your kernel in the kernel land and say, hey, can you open this file for me? And how do you say that? System calls. Cool. So if you want to write something to a file, it's the same idea. So if you see the man page, all the system calls are wrapped in a library called libc, and each language has its own implementation of libc. Rust has two, because why not? So there's the libc crate, and there's an Nix crate, which wraps the libc functions better and in a more idiomatic Rust way. So you have this right man page where you have the function definition of right, and it's copied not word to word, but whatever word would be in this context. In the Rust implementation, where you have a file descriptor and you have the buffer where you want to say, where you put the things that you want to write, and then you have the size of the buffer in the count. And my talk is very geared towards the Linux kernel and x84 architecture, so we should keep that in mind. Yeah, cool. So there are about 330 system calls in Linux. Some of them are very common, like open, read, write. Yeah, we kind of know what they mean, but some of them are very esoteric and widespread. So RD6, maybe that's common too, but some of them you wouldn't ever see in the wild. So let me show you. Whoop. Yes, cool. Sorry. Yeah, I'm here. Sorry. Oh no. Sorry. Give me a second. We get there. No. Cool. No. Sorry. Okay, cool. So let me clear this and pretend that you didn't see it. So I have a test function, sorry, I'll just run test. So test is a binary which just says hello. If I was smarter, it would have said hello RustLab. But never mind. So I'm running strace. So strace is a Linux utility which tells you all the system calls that your binary is making. So I'm just gonna run strace. We get to what strace is. Oh. So it tells you that it was, sorry, yeah. Yeah, it tells you all the system calls that were called when you ran this binary, which are a lot, which we won't care about, but we care about this. Of course, I can't highlight. Oh, I can. Cool. So where you call the write command, the file descriptor is 1 because we're writing to the standard out, and we're writing hello, which is 6 bytes, because you also have an the end of this. I'm forgetting words, but yeah, and it's size 6. So which was helpful, so strace is helpful when you want to debug a sandbox binary where you don't know what's inside the code, but something could be happening where you're expecting it to open XYZ, but it's opening ABC, but you don't know that because you don't have access to the code. So the strace could be very helpful in that context. And yeah, cool. Can I go back? Yeah. So that was me showing you some, showing you some system calls. And then I go, So what actually happens when a system call is called? So let's say you have a write system call, and no, you have a read. You have a read system call, and what you will do is so each system call has a number. So read has the number 9, so you will put 9 into a register, and you push the file descriptor of the file you want to read. You push the buffer saying that's where you want to read. You push the bytes, that's the number of bytes you want to read, and then you transfer to the kernel, and the kernel will look into the register and see this register has the number 9, which means you want to read. Look up the registers which has the bytes and the buffer where you want to read, and it transfers the control back to the user LAN, and then everything's nice and happy. So this is a fairly expensive operation because you are transitioning from the kernel to the user and back, but this is what happens every time you call a read on a file. So, like I said, if you have a system call read, you put the file descriptor in RDI register, you put the buffer in the RSI register, and the count in the RDX register, and then you send a trap to a kernel, and the result is stored back in a register. So there's a standard called the POSIX standard, which ensures that the system calls are same across different architectures, which is helpful because you'd want the same set of standards across different architectures, so you don't have to reinvent the wheel every time. So this is for the read system call across x86, alpha, or ARM, different architectures. You have different registers where you store the arguments. And cool. So now we are onto the part where we want to implement our own strace. So that's what we're gonna do today. So strace uses another system call, which is ptrace. So ptrace allows you to trace another process, change its registers, and examine the contents of the memory and registers, which is all very shady, but that's also what the GDB uses, which is a debugger. So most debuggers use ptrace, and it's fairly powerful and it's fairly powerful system call. So I'm going to go back to the code. Cool. So what we want to do is trace another process. So what we have here is that we pass in a binary to the process, and then we say allow the child to be processed. So here we have a trace me ptrace command. So ptrace has different flags where you have ptrace attach, ptrace detach, ptrace trace me, and trace me will say that allow me to be traced. So I spawn a child and allow the child to be traced, and then once I have the PID, the parent waits for the child to start and starts tracing it. So let's see if it works. It does. Cool. Yeah. Let me go back. So ptrace, you have the tracer and the tracee, and the tracer allows the tracer observes and controls the tracee's execution and can change its registers. And how do you trace a process? So ptrace has a lot of different flags where you can have ptrace attach, detach, trace me, system call, which allows tracing of system calls. And because this is a shady operation, the process which is doing the tracing needs to be in the parent namespace of the tracee. Otherwise, it won't be allowed to trace the program. So either you fork a child, fork, or you have, or the process says trace me, and then you exec. So it's essentially in the parent namespace of the tracee. Every time the tracee stops, you are waiting on the tracee to stop, and then you can go and look around the registers, and you can go around and look at the registers and change them. So you can do peek data, which looks at the data. You can do book data, which changes the data. You can do get register, which gets all the registers of the tracee. You can do trace clone, which allows you to trace the fork and the clone. And you can do trace sysgood, which allows you to only trace the good system calls. No, that's not what it is. It allows you to trace system calls which are not like sigtrap, etc., which can be not the ones that you want to trace. So, I'll just go back to my code. No. Sorry. Sorry. No. Okay, I'll go back. Cool. Cool. So what I have here is an implementation of strace, and I'm gonna walk you through it. Sorry. I'm just going. Cool. So you have something called strace, which shows you the no worries. Which shows you the different counts of each of the system call. So for example, when you run strace on the test binary, you can see that close was called 9 times, fstart was called 7 times, etc., etc. And then, sorry. Oops, sorry. Cool. Can you see things? Yeah. So what I have here is I spawn a child, which is what I need to do if I want to trace a process. And then I say that every time a system call is called or an exec is called by the child, the parent should stop and it can examine things. So, sorry. Yeah. So I have another list where I have all the 300 system calls, and each of those are indexed by the number that the system call has, which makes my life a bit easier. So every time the system call is called, I go and check the original RAX register, and I get the name from the other file, and then I have a map where I increment the system call, and every time a system call is called, I'm tracing on the system call, so every time that is called, I stop, and at the end, so here's the get register functions, get register function, which gets all the registers once the parent is stopped, and here's the get register. Here's where the get register function is used, and then I use that to get the original RAX register. And at the end, I print all the system calls that are called by my function. So, So my aim with this was to demystify how you can do systems programming with Rust, and yeah, this is how you fetch the register values. So there's a lot of unsafe code, and I'm not sorry about that, because libc has a lot of white pointers which you can call. And of course, if you want to call white pointers, you'll have to use unsafe code. So you can do a ptrace get registers, and that's how you get all the registers, and you can see, and sorry. So I just found this, and you can see all the calls that were called by this. And so, yeah, that's me. There are a lot of resources which you can see. And yeah, that's it. Thank you.
Hi. How is Rust handling the changing of system numbers between operating system versions?
I have no idea, because I only implemented it for the kernel, the newest kernel version, and I have a list of the system calls, and I have no idea how this will port to a newer or a different version, but I think there's a crate which you can use, which gives you the correct mapping between the number and the system call name. Does that help answer your question?
Thank you.
Cool.
Any questions? Okay.
Thank you.
Thank you.